Hello everyone. We're going to be talking about a set of notes called Physics and the Quantum Mechanical Model. All right. So, light is one of the things that we need to discuss because we're interested in connecting the idea of something that has a wave-like nature, that light, to electrons. That's the connection that we're going to see. Okay, so light is composed of waves, and these waves have different wavelengths, and we're going to find out what that means in a sec. The wave of light has three characteristics. It's got a wavelength, which is the distance between crests, and I'll show you a picture in a sec that helps you understand that. Then it's got a frequency. In other words, how quickly will a complete wave move past you if you're observing it? And then amplitude, or the height of the wave from the origin. Let me show you the little diagram that I have that helps you understand these. So let's look at the top here where we have this red wave. Um, so I told you the wavelength was the distance between crests of the wave. So here's the wave, here's the peak, the high point, that's the crest, and then it goes back down, and then it comes back up. And this distance between this crest to this crest, that's the wavelength. All right. And then one of the other characteristics that I mentioned was amplitude. So that's the distance from this blue line, which is kind of the halfway point, the blue line, to the peak of the crest. So this distance here is the amplitude. All right. And the third thing that I said was a characteristic of waves was its frequency. And that's a little harder to understand, but let's take a look at it here. I bet we can figure it out. All right, so we imagine this wave is moving along along this blue line here. And let's let this blue line represent a unit of time, like 1 minute. So if we say that this blue line represents, this distance along this blue line represents 1 minute, then how many cycles of the wave move along this blue line in that time span? Well, let's count. Here's the first complete wave. Here's the second complete wave. And then there's half of a third wave. So it's like there's 2.5 complete cycles of the wave in this 1 minute time span. Compare that to this lower, the wave in the lower panel here, the green wave. You can see just by looking at it that it has a much higher frequency because how many complete waves are passing along this 1 minute time span? Well, let's count. Here is 1, here is 2, and 3, and 4, and 5, and 6, and 7, and then maybe another half. So 7.5 cycles of the wave passed in this 1 minute compared to 2.5 cycles for this red wave. So do you see how this green wave is higher frequency? It's moving more quickly through this time across this space here. All right. Also notice or compare the wavelengths between these guys. So the red line might be described as a long wavelength if you compare its wavelength from crest to crest to the green wave's wavelength, which looks much shorter. All right, so you can have high frequency and low frequency. You can have short wavelength and long wavelength. And of course, we don't really demonstrate it very well here, but amplitudes can be different as well. All right, so there's an equation that relates the frequency and the wavelength of light to the speed of light, which is here, c equals h times, this looks like a v, but don't be confused, it's the Greek letter nu. All right, so c stands for the speed of light, and that's a constant, of course, and it's 3 times 10 to the 10th centimeters per second. And the wavelength, which we just talked about, is usually measured in centimeters or meters, but you can measure it in other units as well, nanometers, for example. That's the distance between crests. And then nu is the frequency, and we measure that in 1 per second, or hertz. The hertz is defined as 1 over seconds, and that's how many, in other words, how many waves pass a given point in 1 second. So that's the measure of frequency. Okay. Let's take a quick look at the electromagnetic spectrum itself. It ranges from the very, very short wavelength of a gamma ray to the rather long wavelength of the AM radio wave. And everything falls in between there somewhere. Visible light is this skinny little piece right here, which I've pulled out into a larger section down here. So this is the part that we see with, but all these other things, all these other segments of the electromagnetic spectrum you should probably be familiar with as well. You've heard of gamma rays and X-rays and so on. Right? They're all part of the same spectrum. Visible light, like I said, is only a small piece, around 400, 700 nanometers in the center of the electromagnetic spectrum. This is the part that allows us to see, and it can be divided into colors based on these wavelengths, with red, yellow, green, blue, indigo, and violet being the various colors, where violet is the highest energy and red is the lowest energy. Well, so what? Why do we care? Well, because we're interested in electrons at this point. We're moving into our section on bonding, and so we really care about electrons. Why am I talking about light? Um, well, remember electrons have orbitals, right? And the visual that we had for that was Bohr's planetary model, where electrons were imagined to be moving around the nucleus in an orbit. Now, that's not perfectly accurate, but it's a pretty good representation. And then the other piece to that is that the closer the electron is to the nucleus, the lower energy it is, and the further out, the higher energy it is. Okay. So if an electron is allowed to absorb some energy, it can become it can go from a lower energy electron to a higher energy electron. It can do that by absorbing some energy, and it moves from a closer in orbit to a further out orbit. All right, it has to absorb a certain amount of energy. It can't absorb any random amount. There's a very discrete amount of energy that an electron can absorb to move from one orbital to another, and that's called a quantum. Quantum can be thought of like a packet or a set amount of energy. So you can't have any random amount. It's a very specific amount of energy that an electron can absorb to go from one orbital to the next outer orbital. This energy can be absorbed from a photon, so possibly an electron can absorb the energy of a photon, or from heat, or from electricity. And this process, of course, is called absorption. So you can excite an electron from a lower energy orbit into a higher energy orbit by allowing that electron to absorb some energy, a very specific amount of energy called a quantum. All right, we're getting closer. So once you have a high energy electron, it can relax into a lower energy state by a process called emission. This gives off a quantum of energy. So you see the connection there? Absorption, you had to absorb a quantum of energy. Emission, you're going to give off a quantum of energy. And in doing so, the electron will relax from a high energy state into a lower energy state. When you give off a quantum of energy, typically this is a photon, which of course is light. And so if you've got a sample of an element, like hydrogen, for example, on the next slide, there's an example. If you excite the electrons in hydrogen and then allow them to relax, they will give off photons of light in a characteristic spectrum. Each element has its own characteristic electromagnetic emission spectrum, and the spectrum for hydrogen is different than the one from helium, than the one from argon, and so on. This is a quick example of that. So here's what's called a hydrogen lamp. It's a glass tube filled with hydrogen gas, and you run electricity through it. That electricity stimulates or empowers that's not the right word. Stimulates the electrons, allowing them to absorb energy and move from low energy state to high energy state. And then when those electrons subsequently relax, they give off a photon of light. They emit a photon of light. If you pass this light through a slit and then into a prism, you can split the light into different colors of light. And this is what I mean when I say an element has a characteristic emission spectrum. This is the one that you get from hydrogen. There's a reddish colored line here, and a bluish one here, and more green here, and then indigo. I've got those backwards. This is green, and this is blue, and this is indigo. You get a different set of lines for a different element. Helium will have a different set of lines. Argon will have a different set of lines. Calcium will have a different set of lines. So the emission spectrum that is emitted when electrons relax after being excited is different from one element to the next. Okay, so now we've been talking about an electron absorbing some energy and then giving it off as a photon of light. But for some kinds of metals, when you shine light on them, the electrons absorb energy, like we just talked about, but they don't move to a higher energy level. Instead, they're ejected from the atom. They're kicked out. So certain metals will eject electrons when light shines on them. All right? So I think I have a little animation next. Let's see if it works.
When light strikes a metal surface, electrons may be ejected. This process is called the photoelectric effect. Each metal has a characteristic energy level. If the incoming light is below this level, no electrons will be ejected. For example, this red light is not sufficiently energetic to eject electrons from cesium metal. Yellow light is also not energetic enough to eject electrons. Green light is energetic enough to eject electrons and current flows.
Okay, so the point here was a quick description of what the photoelectric effect is. That's where you shine a light on certain kinds of metal and it will eject electrons and make a current flow. But it doesn't absorb just any kind of light. It has to be a specific wavelength. Now, this concept or this observation was studied by a guy named Max Planck in the early 1900s because it struck him as odd that only certain wavelengths would work. He didn't understand if light was a wave, why should it matter what wavelength the incoming light was for this photoelectric effect to happen? So he developed a relationship between energy and frequency that helped to explain this. You remember frequency, right? We talked about this earlier in the slide with the long wavelength, the short wavelength, and then the frequency is that you're counting how many times it passes over a given point. Remember that? All right, that's frequency. Okay, so this guy Planck came up with an equation, because that's what they used to do, make an equation, and with a constant in it. So the energy, E, the energy of the photon, is related to Planck's constant, sorry, it's supposed to be Planck's constant, and the frequency of the radiation, measured in hertz. So Planck's constant is 6.6262 times 10 to the minus 34th joule seconds. That's a constant value, like the speed of light is a constant value. So the energy of a wavelength of light is related to its frequency by Planck's constant. Just as a quick reminder, we can also relate frequency and wavelength of light to the speed of light. All right. So there are two different ways to discuss the energy of a wavelength of light. All right. So the upshot, the conclusions from Planck's work was that light could behave as a wave and as a particle, since it had the ability the photoelectric effect showed that light could sort of act like a particle because it could knock an electron off of a certain kind of metal. But also, we all know that light is a wave. So Planck's work showed that light could behave as a wave and as a particle. And in the mid-20s, there was another scientist named de Broglie, I'm probably saying that wrong, who wondered if the same thing could be true of electrons. So he developed a relationship between mass, wavelength, and velocity, and demonstrated that electrons could, in fact, have a dual nature, a wave-particle nature. Here is de Broglie's equation. The frequency is equal to Planck's constant divided by the mass of the particle, m, and here we've got velocity, v. This is not the same kind of, and I know they look alike, so be careful. This is the v for velocity, not the Greek letter nu for frequency. Don't get confused. All right, so here's velocity, and then mass, and there's wavelength. So this is the de Broglie equation, or the de Broglie relation. And he developed this by thinking about Planck's work and wondering whether electrons could have a dual nature. So de Broglie's conclusions were that that was true. Electrons can behave as wave and as particle. And he also wondered, can this be true for other matter, or is it just electrons? And as it turns out, it's true. This relationship holds for other kinds of matter. For example, a baseball has a dual wave particle nature. Here's a baseball. So here is de Broglie's relation, frequency, lambda equals Planck's constant divided by mass times velocity. All right. And so the mass of the particle in this case is a baseball, which is around 145 grams. And let's say that baseball is being thrown by a pitcher who is, maybe this the change-up pitch because it's pretty slow, 60 miles per hour. We'll convert that to meters per second, which you all know how to do because we just did dimensional analysis. So 27 meters per second is our velocity. We have our mass and our velocity. And then here's Planck's constant again, just to remind you what that is, 6.6262 times 10 to the minus 34th joule seconds. If we plug these numbers into de Broglie's relation for this baseball, we get that the wavelength of a baseball, lambda, is 1.7 times 10 to the minus 34th meters. Okay, so what this shows is that all matter, even macroscopic things like a baseball or a desk, have a wavelength. But we can't easily observe that wavelength because it's super duper, super duper, super duper small. 10 to the minus 34th meters is astonishingly small. So we have no way to measure that frequency. We only have a way of, I'm sorry, not frequency, wavelength. We can only calculate it. Okay, so we're going to do after tomorrow in class, we're going to do some calculations about um, using the light equations and using de Broglie's relationship and Planck's constant. We'll do some examples of that tomorrow in class. And I think that's it for now.